Imagine it is 9 a.m. on a Monday. Your CI/CD pipeline starts failing because your LLM-based code reviewer is returning a 403 forbidden or for a 29 too many requests error. Overnight, the vendor changed their regional policy, or your Tier 4 usage limit was suddenly throttled back to Tier 1 without any warning. In the industry, we call this the cloud AI hostage situation. When your core productivity depends on a third-party API key, you are not just renting a model, you are outsourcing your company's intelligence to a black box that can be switched off by a bean counter 3,000 miles away. We have seen this happen repeatedly: sudden API price hikes, regional geo-blocks for models like Claude, or capacity-reached errors during peak hours that bring development to a screeching halt. Even with a bottomless budget, you do not own the weights, you do not own the uptime, and you certainly do not own the roadmap. But weight is the solution, just paying for a more expensive enterprise plan. By the end of this lecture, you will see why that is a trap and how to reclaim your sovereignty. A few years ago, running a decent coding model locally required a rack of 100 GPUs and a PhD in prompt engineering. Today, in 2026, the landscape has shifted entirely. We have reached a point where local AI is no longer a compromise. It is a strategic advantage. We are seeing models like Llama 3.18b or Mistral Nemo being quantized down to 4-bit GGUF formats that fit comfortably within a standard 8GB, 12GB VRAM setup. Think about it: zero latency, zero token costs, and 100% to offline availability. I see teams wasting thousands of dollars monthly on Claude 3.5 Sonnet tokens for simple boilerplate generation that a local 7B or 12B model could handle with 98% accuracy. Using tools like LM Studio or Llama combined with VS Code's Continue extension, you can build a development environment that works on a plane, in a secure bunker, or during a total ISP outage. This is the promise of the cloud AI exit, moving from a subscription model to an asset ownership model. But wait, is a cheap consumer GPU really enough to match the reasoning power of a trillion-parameter cloud model? Let's look at the cold, hard numbers that managers often ignore. A typical mid-sized dev team of 20 engineers using high-end cloud APIs can easily burn through $3,000 to $5,000 a month just on chatting with code and automated refactoring. Over 2 years, that is over $100,000 more than enough to buy a dedicated GPU cluster for the entire office. Then there is the privacy elephant in the room. Every time you send a proprietary function or a sensitive database schema to a cloud endpoint for optimization, you are effectively leaking intellectual property into a third-party training pool, regardless of what the enterprise agreement promises. In high-security environments, this is often a non-starter. Local LLMs solve this by keeping every single byte of data within your system's RAM. You gain absolute privacy, predictable zero-cost scaling, and the ability to fine-tune on your own private codebase without any external exposure. This triple threat of cost, access, and privacy is why the smartest teams are pivoting away from the API-first mindset. However, is privacy the only reason developers are making the switch? Why are we talking about the cloud exit specifically in 2026? Because we have reached a critical hardware-software convergence point. In 2023, local LLMs were a hobbyist's toy. In 2024, they became usable for basic Python scripts. By 2026, the distillation revolution has allowed us to compress the reasoning capabilities of massive models into small, AB to 14B parameter footprints that run natively on NPU-equipped laptops. We have moved from the era of big models to the era of efficient inference. We now have specialized opencode models that outperform the original GPT-4 on complex Rust or Go tasks while running entirely in your local VRAM. This timeline shows that the gap between local and cloud is no longer a canyon. It is a small crack you can easily step over. If you are still building your 2026 roadmap around a single API provider, you are building your house on quicksand. So, how do we actually start building this local infrastructure without losing the magic of AI coding assistance? In the next chapter, we will move from why to how as we architect your first high-performance local AI stack. When you decide to ditch the cloud and go local, you are immediately hit with an overwhelming sea of GitHub repositories and awesome local AI lists. In the field, we don't have time to experiment with everything. We need a reliable, production-ready stack that works as a cohesive unit. For our cloud exit architecture, we rely on 3 pillars: LM Studio as our local inference engine, Continue Dev as our ID orchestration layer, and specialized models like OpenCode or DeepSeek Coder. LM Studio acts as the heart, hosting models and providing an OpenAI-compatible local API server. Continue Dev sits inside your VS Code or JetBrains IDE, acting as the brain that directs the model to read your files. This setup isn't just about avoiding costs. It's about building a private, latency-free development environment that exists entirely within your firewall. But simply picking these tools isn't enough. You need to understand how they compete against each other in real-world scenarios. Which one of these 3 actually consumes the most resources during a heavy coding session? Let's break down the metrics. Most tutorials tell you what to install, but they rarely tell you why it might fail. From my experience in high-pressure environments, the choice between LM Studio and Llama comes down to a trade-off between user interface and raw throughput. LM Studio is the gold standard for debugging. It gives you a visual GUI to monitor VRAM usage and token generation in real time, which is critical when you're first tuning your agent. Llama, on the other hand, is built for those who prefer the CLI and need a lightweight footprint for background services. When we look at agent support, continued dev stands alone because it allows for context providers, meaning it can index your entire codebase locally without sending a single byte to an external server. You must evaluate these tools across 4 axes: setup difficulty, inference performance, memory overhead, and native agent capabilities. If you choose a tool that's too heavy for your RAM, your IDE will lag, and your productivity will drop below what it was with a simple cloud API. But wait, what if your hardware is the bottleneck? I'll show you exactly what model fits your specific machine next. Hardware is the ultimate reality check for local AI. You cannot run a 70 billion parameter model on a 16 GB MacBook Air. It simply won't work, or it will generate one word every 10 seconds. In the field, we categorize hardware into 3 tiers. Tier 1 is the starter level, like an 8GB or 16GB consumer laptop. Here, you're limited to 7B or AB models like Llama 3 or Mistral, heavily quantized. Tier 2 is the professional level, featuring 32GB to 64GB of RAM. Think Mac Studio or dual RTX 3090s. This is the sweet spot where you can run DeepSeek Coder 33B with enough speed to actually feel like you're using GPT-4. Tier 3 is the enterprise level with 128 GB RAM, allowing for unquantized massive models. The trick is VRAM allocation. If your model exceeds your VRAM, it spills over to system RAM and your performance falls off a cliff. Understanding this mapping is the difference between a smooth coding experience and a frustrating wait time. But even with the right hardware, how do these tools actually talk to each other? Let's look at the infrastructure logic behind the scenes. To build a seamless local agent, you need to understand the backend bridge logic. When you type a prompt in VS Code, the continue extension doesn't just process text. It gathers context from your current file terminal and Git history. It then packages this into a JSON payload and sends it to the LM Studio local server via an HTTP POST request. LM Studio, acting as our inference engine, receives this request, loads the model weights into your GPU, and streams the generated tokens back to the IDE in real time. This loop must be low latency to be usable. We use the OpenAI-compatible API format because it's the industry standard, allowing you to swap out LM Studio for a Llama or even a remote private server without changing a single line of your IDE configuration. This modularity is key to a future-proof cloud exit strategy, but there is a secret to making these heavy models fit into consumer hardware without losing their intelligence. That secret is quantization, and it's often misunderstood. Quantization is what makes the impossible possible. A typical high-end coding model in its original 16-bit floating point format might require 80 gigabytes of VRAM, well beyond what most of us have. By quantizing the model to 4-bit GGUF format, we reduce the memory requirement by nearly 75% with only a negligible loss in coding accuracy. Think of it like a high-quality JPG vs a RAW photo. For most coding tasks, the compressed version is indistinguishable. We primarily use the GGUF format because it's highly portable and allows for layer offloading, where you can run part of the model on your GPU and the rest on your CPU if you run out of VRAM. There is also EXL2, which is faster for pure GPU setups, but GGUF is the most reliable for mixed hardware. If you ignore quantization, you'll likely face out of memory errors before you even finish your first line of code. But even a quantized model can fail if you don't manage the context window correctly. Does a larger window always mean better code generation? The final piece of our architecting puzzle is the context window and system prompt optimization. The context window is the short-term memory of your AI. In a local setup, every extra token you add to the context window consumes more VRAM. If you set 32,000 tokens on a limited GPU, the inference will slow to a crawl. For coding agents, we find the sweet spot is around 8,000 to 16,000 tokens. This is enough to hold your current file and a few related modules without crashing the system. Additionally, we must use specific system prompts that tell the local model to act as a concise senior engineer to avoid the rambling tendencies of smaller LLMs. We've now built the blueprint, the tools, the hardware mapping, the backend loop, and the compression secrets. You have the what and the why, and it's time to actually get our hands dirty. In the next chapter, we are going to perform a live, zero-cost deployment from scratch, no credit card, no cloud, just your machine and a few commands. Ready to see this stack in action? You are probably tired of seeing those API quota exceeded messages right when you are in the middle of a flow. In the real world, relying on a cloud provider for your basic coding cycles is a strategic risk. Let's fix that by setting up LM Studio. First, you download the binaries, but don't just click Next blindly. We are looking for the local server tab on the left sidebar. This turns your machine into an OpenAI-compatible endpoint. Why does this matter? Because almost every modern AI agent tool expects the OpenAI API format. By hosting this locally, you're tricking your tools into thinking they're talking to a billion-dollar cloud infrastructure, while in reality, it's just your silicon doing the heavy lifting. But wait, setting it up is the easy part. The real challenge is making sure the server doesn't crash your entire OS when you start a long context window. Do you know which port is safest to avoid conflicts with your existing web dev servers? We will cover that right now. But simply having a server isn't enough. It's like having a car without an engine. Next, we need to pick the right brain for this machine. Choosing a model isn't about picking the one with the highest number of parameters. In a production environment, you need a balance between intelligence and inference speed. For coding, I always recommend DeepSeek Coder v2 or Codalama in GGUF format. Why GGUF? Because it allows for sophisticated quantization. If you have 16 GB of RAM, don't even think about running a 70B model. You'll be waiting 10 seconds for a single semicolon. Look for Q4KM or Q5KM versions. These are quantized models that retain about 98% of the original logic while cutting the memory footprint by half. I've seen juniors try to run the F16 original weights on a laptop and then wonder why their fans sound like a jet engine. We are aiming for a sub-second time to first token. If your model takes 5 seconds to respond, you'll lose your train of thought and go back to GPT-4. But is a fast model always a smart model? Let's look at the benchmarks that actually matter for developers, not just the academic ones. You might be surprised at how a smaller, specialized model outperforms the giants in specific languages like Rust or Go. Now, let's talk about the secret sauce that separates the pros from the amateurs: GPU offloading. Most people just run everything on the CPU and complain that local AI is slow. If you have an NVIDIA card or an Apple Silicon chip, you must distribute your model layers properly. In the Studio settings, look for the GPU offload slider. You have 8 GB of VRAM, you can usually push about 20 to 30 layers of a 7B model onto the GPU. This offloading can increase your tokens per second by 5x or even 10x. I've seen builds where the developer was getting 2 tokens per second, but after tuning the layer distribution, they hit 40 tokens per second. That's the difference between a frustrating tool and a seamless partner. However, you push too many layers, the system will run out of memory and crash your entire desktop environment. It's a delicate balance. I'll show you a table of sweet spots for common hardware configurations I've tested in the field. But even with a fast engine, how do we know if it's actually producing valid code or just hallucinating at high speed? Next, we'll verify the health of our local endpoint. Before we move to the IDE, we need to prove our local setup is ready for work. A simple way to check is using a basic QRL command against the local endpoint. We are looking for 3 things: total response time, token generation speed, and most importantly, the consistency of the JSON structure. In the field, I often see zombie servers that stay up but return empty responses or garbled text because the quantization went wrong. If your time to first token is higher than 2 seconds, you need to go back and reduce the context length or increase GPU offloading. A healthy local setup should feel instantaneous for short snippets. I once worked on a project where we cut our dev cycle by 30% just by switching to a local model because we didn't have to wait for the high latency cloud round trips. It's not just about cost, it's about the feedback loop speed. Now that our engine is validated and purring, it's time to plug in the steering wheel. This is where we integrate the local server with VS Code. Do you think it's as simple as changing a URL? It's a bit more nuanced than that, as you'll see in the next section. Now we bridge the gap between our model and our code. We'll use the continue extension in VS Code. It's the industry standard for open source AI agents right now. Most people get stuck here because the configuration isn't in the GUI, it's in a hidden config JSON file. You need to tell continue to stop looking for an OpenAI key and instead look at your localhost. Notice the API-base field in the code block. This is the magic link. If you miss a trailing slash or misspell the model name as it appears in LM Studio, the agent will just hang silently. I've wasted hours debugging why my agent wasn't responding, only to find out it was looking for localhost 2134 v1 chat instead of just v1. Pay close attention to the model provider field. We set it to OpenAI even though it's local, because we are using the compatible protocol. This is how you get the best of both worlds. Premium features with 0 subscription cost, but an agent that only sees the current file is useless for large projects. How do we make it understand your whole architecture? That's what we tackle next. Standard AI assistants often hallucinate because they lack context of your project's unique structure. This is where local RAG retrieval augmented generation comes in. Continue can index your entire codebase locally using a library called LancyDB. This happens purely on your machine. No code is ever uploaded to a server. When you ask, where is the auth logic, the agent doesn't guess. It searches your local vector index and finds the actual files. You should configure a .continueignore file similar to igitignore, so the agent doesn't waste time indexing your node modules or dist folders. I've seen developers complain that the agent is slow, only to realize it was trying to index 2 GB of dependencies. Once properly indexed, the agent gains architectural awareness. It becomes a senior partner who knows the codebase as well as you do. But how do you interact with this newfound intelligence efficiently? Just chatting isn't enough. You need shortcuts that match your workflow. To really speed things up, you need to master slash commands. These are predefined prompt templates that save you from typing the same instructions over and over. Commands like edit for refactoring or test for generating unit tests are game changers. In the local setup, these commands are even more powerful because they are nearly free to run. You can also create custom commands for your team's specific standards. For example, if you have a strict linting rule or a specific way to write documentation, you can bake that into a docs command. In my experience, teams that use standardized slash commands have 40% fewer PR comments because the AI enforces the style guide before the human even sees the code. It's about building an automated guardrail that lives in your IDE. This is where the zero-cost aspect really shines. You can experiment with complex prompts without worrying about the bill at the end of the month. Ready to see the results? Let's verify our setup with a real-world coding task, completely offline. This is the moment of truth. We're going to perform a first local commit. I've seen this succeed in some of the most restricted environments, places where even the internet was blocked for security reasons. We ask the agent to refactor a function, it scans our local index, applies the change via LM Studio, and we review it all in a matter of seconds. No data left our network. No credit card was charged. We've successfully exited the cloud AI dependency. This isn't just a hobbyist setup. It's a professional-grade development environment that respects your privacy and your wallet. If you followed along, you now have a localized powerhouse. However, while local AI is amazing, it's not always sunshine and rainbows. Sometimes models go rogue or memory leaks happen when you least expect it. In the next chapter, I'm going to share some real battle stories, the kind of failures you only see after running these local agents in production for months. You'll want to hear this before you roll this out to your entire team. In the local LLM world, you'll encounter a phenomenon I call the slow death syndrome. You start your coding session at 9 a.m. and everything is snappy. By 4 p.m., your 2026 Spec Max Studio is lagging and inference takes twice as long. This isn't a software bug in your IDE, it's VRAM fragmentation. Unlike system RAM, VRAM allocation for large language models is incredibly sensitive. When you're constantly swapping between a 7B coding model and a 14B reasoning model, QDA or Metal doesn't always release blocks cleanly. These ghost allocations eat into your contiguous memory space, forcing the system into aggressive swapping. If you don't understand the physical limits of your hardware, your local cloud exit will feel like a performance downgrade within days. It's the first hard lesson. Hardware management is now part of your DevOps responsibility. Let's talk about context bloat. Cloud providers like OpenAI or Anthropic use massive clusters to hide the quadratic cost of attention. Locally, you are the cluster. When your context window hits 32K or 64K tokens, the KV, the memory of your current conversation, starts competing with the model weights for VRAM. I've seen developers try to feed an entire 100-file repository into a local agent. The result? The model starts forgetting the beginning of the file, or worse, the system triggers an out-of-memory kill. In the cloud, this just costs you more money. Locally, it crashes your entire development environment. You have to be ruthless. You must learn to architect your prompts to include only what's necessary. In 2026, context density is a much more valuable skill than prompt engineering. To survive an A-Router coding marathon, you need a maintenance routine. I use a zero-trust memory policy. First, implement KV cache quantization. Switching your cache to 4-bit can save gigabytes of VRAM with negligible logic loss. Second, set up a warm restart trigger. My IDE is configured to restart the local inference server, like Ollama or LM Studio, every time I'm idle for more than 15 minutes. It clears the fragmentation and starts fresh. Third, use a sliding window for your conversation history. Don't let the agent remember the conversation from 3 hours ago. It's irrelevant and toxic to your performance. These steps convert a fragile local setup into a production-grade workstation that stays snappy until your last commit of the day. Let's be honest, a local 7B or 14B model is not Claude 3.T5 or GPT-4o. It will hallucinate imports, invent non-existent API parameters, and occasionally lose the plot on complex logic. However, the cloud exit is about matching raw brain power. It's about context relevance. A local 7B model that is perfectly integrated with your project's documentation via RAG, retrieval augmented generation, will often produce more accurate, compile-ready code than a 70B cloud giant that doesn't know your internal libraries. The gap between small and large models is closing, but you must bridge the remaining distance with context injection. Don't ask the model to be smart. Give it the exact documentation it needs to look smart. This is the core strategy of the 2020s engineer. How do you trust code written by a local model? You don't. You build a verification loop. In my workflow, the agent doesn't just output code. It's forced into a TDD, test-driven development cycle. The agent writes a function, and then it's immediately piped into a local linter agent or a compiler agent. If the code doesn't pass NPM test or cargo check, it goes back for a retry automatically. This loop happens entirely on your machine, so it's nearly instantaneous. By the time you look at the screen, the agent has already failed, learned from the error message, and fixed its own hallucination. This self-correction loop is the only way to scale local coding agents without spending your whole day debugging AI garbage. Ultimately, as a 2026 senior engineer, your role isn't writer, it's architectural auditor. Local agents are brilliant at the how, but they are historically terrible at the why. They might give you code that works, but it might also introduce a circular dependency or violate your project's clean architecture. You are the final gatekeeper. Your job is to verify that the agent's output aligns with long-term maintainability. Don't be seduced by the speed of local generation. Use that saved time to think about the bigger picture. If the agent saves you 4 hours of typing, spend one of those hours doing a deep dive architectural review. This is how we maintain high standards while moving at the speed of local AI. In the field, I see many developers falling into the model perfectionist trap. In 2026, with base models like Llama 4 or DeepSeek V4 being incredibly capable out of the box, the biggest anti-pattern is obsessive fine-tuning. I once saw a team spend 3 weeks trying to fine-tune a 7B model to follow a specific JSON schema, when a simple system prompt and a slightly larger 32B model would have solved it in 10 minutes. They were so focused on shaving the model size that they missed their production deadline. Another mistake is using deprecated quantization methods like 2-bit or 3-bit GGUF for coding tasks. These destroy the logic reasoning of your agent. If your agent is hallucinating code, it is often not the prompt. It is that you have compressed the model until it lost its core reasoning. Stop trying to build the perfect model and start building the perfect workflow. The market moves faster than your training loops. But wait, even with a great model, are you sure your local setup isn't a ticking time bomb for your company's data? Security is where local AI setups often fail silently. When you run an inference server like Ollama or VLLM locally, it's tempting to open ports so your teammates can share the GPU. However, if you don't set up a proper reverse proxy or a VPN, you're essentially giving anyone on the network a direct line to your file system via the agent's tool use capabilities. In 2026, prompt injection is no longer a joke. It is a vector for moat code execution. If your agent has access to a terminal or a file write tool, a malicious prompt can trick it into running scripts that exfiltrate your denv files. I've seen developers leave their local AI endpoints exposed to the public internet without even a basic API key. Always use a local firewall and strictly limit the search and execute scopes of your coding agents. Never give your agent root access to your machine, even if it is just for debugging. If you think your local setup is safe just because it is local, you are in for a rude awakening, but how do you actually turn these risks into a career advantage? Being a senior engineer in 2026 means moving beyond just writing code. You must become an AI infrastructure orchestrator. The industry is splitting into two groups: those who just use tools and those who build the sovereign stack. This involves managing local RAM allocation, understanding KV cache optimization, and knowing which quantization formats GGU EXL2 or AWQ is optimal for your hardware. I've noticed that engineers who understand the underlying compute are the ones leading the most successful AI migrations in their organizations. They don't just ask for a GPU. They know how to scale a local cluster using tools like Kubernetes for local inference nodes. This sovereign approach ensures that even if a major cloud provider changes their terms of service or blocks your region, your team keeps shipping. It is about owning the means of production, but is going 100% to local always the smartest move for every single task? The answer might surprise you when we look at the hybrid reality. The most practical architecture for 2026 isn't local only, it's local first hybrid. Use your local machine, your Mac Studio, or your multi-GPU rig for 90% of your daily coding, iterative testing, and privacy-sensitive logic. This keeps your costs at zero and your latency at instant. However, for massive refactoring tasks that require a 2 million token context window or highly complex architectural validation, you must have a cloud-burst fallback strategy. This means writing your agentic frameworks to be model agnostic. If the local model struggles with a specific logic gate, the system should automatically route that request to a heavyweight CLI API like Claude 4 or GPT-T5 for a single high-precision hit, then return to local for implementation. This balance provides the ultimate cost efficiency and privacy without sacrificing raw power. We've covered the rules and the pitfalls, but how do you actually chart your path to becoming this sovereign developer? In the next chapter, we'll build your personal roadmap to technical independence. Look, the biggest mistake developers make is finishing a masterclass and never actually opening their terminal. In the real world, knowledge without execution is just noise. Tonight, your mission is simple: download LM Studio and treat it as your local API server. Pull the DeepSeek Coder V2 or the latest Llama 3 variants in GGUF format, aiming for Q4 or Q5 quantizations to balance speed and intelligence on your hardware. Integrate this into VS Code using the Continue extension so your workflow remains uninterrupted. This setup is your emergency exit from the cloud dependency trap we discussed earlier. You are no longer just an API consumer, you are an infrastructure owner. This is how you build a resilient, private development environment that works regardless of price hikes or service outages. But installing the tools is only the entry ticket. How do you stay ahead when the ecosystem shifts again next week? We've covered everything from the cloud API exit strategy to the actual implementation of local agents. The journey to becoming a sovereign developer isn't just about saving money on tokens. It's about reclaiming your autonomy in an era where data privacy and service reliability are increasingly fragile. You now have the roadmap to run high-performance models on your own silicon, bypassing the gatekeepers. As we look toward the rest of 2026, the trend is clear. The most valuable engineers won't be those who can just write a prompt, but those who can manage the entire local lifecycle of an AI agent. This concludes our guide on the cloud exit, but the rabbit hole goes much deeper. Now that you can run these models locally, the next logical question is, how do we make them absolute experts in your specific proprietary codebase? In the next series, we will dive into the mechanics of local fine-tuning, training your own ghost in the machine,